Hey there, future physicists. Let me ask you a question. Have you ever tried to unbake a cake? Or maybe, have you noticed how a piece of ice melts into water but can never go back to being ice without freezing it again? Well, that's what we are diving into today, the fascinating world of reversible and irreversible processes. You see, in the universe of thermodynamics, things change, and we try to understand how and why these changes happen. Some changes, like melting ice, happen naturally and can't be undone. Those are irreversible processes. But then there are reversible processes which happen so smoothly and perfectly that, in theory, they can be reversed. So, let's explore these processes and see how the second law of thermodynamics plays a role in them. Let's start with reversible processes. Picture a super slowly moving piston in an engine. In a reversible process, everything happens at a perfectly controlled pace, so slow that the system is always in equilibrium. Imagine a gas expanding in a cylinder with every step perfectly balanced. This means no energy is wasted, no heat is lost, and the process can be reversed by just the tiniest change. The key here is that in a reversible process, no entropy is generated. That's right. The system returns to its original state without leaving any trace of the process. In fact, we use this idealized concept to model how things should work in a perfect world. Now, let's look at the other side, irreversible processes. This is where things get interesting. Most of what we encounter in everyday life is irreversible. Imagine compressing a gas quickly. No matter how much you try, it won't just return to its original state without some effort. When energy flows quickly, it's hard to reverse. For instance, when you put your hot coffee on the table, it cools down. That's an irreversible process because the heat moves from the coffee to the surroundings and you can't easily reverse it. These processes create entropy, and once it's created, it's gone forever. That's the law of nature at work. So, why is entropy such a big deal in reversible and irreversible processes? Well, entropy is a measure of disorder. And guess what? The second law of thermodynamics says that in any irreversible process, entropy always increases. This is the heart of the second law. Systems tend to evolve toward higher entropy or higher disorder. In a reversible process, there's no net change in entropy, but in irreversible processes, entropy increases. Think of it like this: when your ice cube melts, it's spreading out its molecules and increasing the disorder in the system. That's an increase in entropy. The second law tells us that once disorder increases, it's practically impossible to get it back to the original state without putting energy into the system. Let's solidify these concepts with a real-world example. Imagine a 1 kilogram block of ice at minus 10 degrees Celsius, and we are heating it up to 0 degrees Celsius. The specific heat capacity of ice is 2.1 joules per gram per degree Celsius. How much does the entropy change during this process? First, calculate the heat added using the formula Q equals m times C times delta T. Now, substitute the values. Q equals 1000 grams times 2.1 joules per gram per degree Celsius times the difference between 0 degrees Celsius and minus 10 degrees Celsius, which is 10 degrees. This gives us Q equals 21,000 joules. Now, calculate the change in entropy. Delta S equals Q divided by T. So, delta S equals 21,000 divided by 273, which is approximately 77 joules per Kelvin. Thus, the change in entropy is 77 joules per Kelvin. This tells us that the ice is getting more disordered as it heats up, just like the second law predicts. Quick insight: as heat is added, the system becomes more disordered and entropy increases. To sum up, Reversible and irreversible processes are the two main ways that energy flows and changes in thermodynamics. While reversible processes are idealized and maintain equilibrium, irreversible processes happen naturally, leading to an increase in entropy and making them practically impossible to reverse. The second law of thermodynamics governs all these processes, telling us that the universe is always moving towards more disorder. So, the next time you boil water or heat up some leftovers, remember, it's all a dance of entropy, and those messy, irreversible processes are the ones driving most of the world around us. See you next time with another exciting topic in physics.